is because we don't always have an equation we're working with. Yeah, so that's the only reason I stick to this one, because this will work even if it wasn't an equation. Okay, so there's my hidden 0, right? That's why I'm not changing the integrity of the problem. And then 3, and then z squared minus 4z. And for this one, I'm going to take half of that, which is -2, add and subtract it, or square it, add and subtract. So I'm adding and subtracting 4. And then what do we still have? Equals 10. Sorry about that. And that allows me to go ahead and continue through. I'm going to go back on this one, just write 3x squared. Here plus 3. OK. What's the point of completing the square? Like, what was the point of all that? What are we guaranteed is going to happen now? These 3 right here are guaranteed to be perfect square trinomial, right? Or that is a perfect square trinomial. So what I can do is turn that into y minus 1 squared. But then I still have minus 1. Everyone see that? And then over here, we have same thing. These 3 will turn into what? Something squared. What is it? Z minus 2. And then minus 4. Notice I have to keep my parentheses, right? Because of this 3 out here. Got to keep these parentheses. Now you pass through your parentheses, or your 3's through. So when I do that, this will go here. It's just going to plop in front of the parentheses here. It'll go to here. This one will go in front here, and this will go here. So we have 3x squared plus 3 times y minus 1 squared minus 3 plus 3 times z minus 2 squared minus 12 equals 10. We're getting close. I'm going to take all the numbers and move them to the other side. So I'm going to add 15 to both sides. Sound good? Now, when you had said you just multiply by 3 and add to both sides, that's actually happening right now. So it works both ways. So plus 3. While I'm finishing this up, does anyone have any questions about this? Now, divide by 3. There you go. So divide by 3, x squared plus y minus 1 squared plus z minus 2 squared equals 25 thirds. Does that look like the form of a sphere, the equation of a sphere? Yes. And so we should just be able to look at that now and say what the center is. So what is the center of this sphere? What is it? 0. It comes from there's nothing next to that. Then 1, and then 2. What's the radius of this sphere? It's the square root of that, right? Which is 5 over root 3, which you could leave as 5 root 3, or 5 over root 3, or you could rationalize it. Doesn't matter. Make sense? So that's a homework problem. You know, if I wouldn't have shown you that, you might have looked at it and go, what the heck do they want there? They want you to turn the equation into something that looks familiar to you so you can extract the center and the radius from it. To do that required some completing square. There's another problem in the homework. I'm not going to put it up here and do it. There's another problem in the homework where they give you three points. So they actually give you, like, I don't know what they are, 2, 5, 7, then some other point and some other point in three-dimensional space. And they ask you to find the distances between the points. So they call this like point A, B, and C. Ask you to find the distance between A and B, then between like A and C, and then between C and B. And then they ask you this question: is that a right triangle? How would you determine if that's a right triangle? What's that? If they were all the same, it would be an equilateral triangle, wouldn't it? Right?
2 points would have to be on the same plane.
Not necessarily, right? I mean, think about, they don't have to be on the same. Trying to think of what you just said. Would 2 points have to be on the same plane? No. They have to be on the same line. But so what I heard, what would have to happen? They would have to follow the Pythagorean theorem, right? A squared plus b squared would have to be c squared. That's what it would require for it to be a right triangle. So you're going to figure out what each of these lengths are, and you're just going to check the Pythagorean equation on it. Does it check out or not? If it is a right triangle, there's going to be a longest side, right? A hypotenuse. That'll be your potential C. The other two sides would be your A and B. So let's just say this had turned out to be 7, 9, and 11. Let's just say. And they're asking, is that a right triangle? Then you'd be checking that 9 squared plus 7 squared equals 11 squared. If it doesn't check out, it's not a right triangle. Understand? Okay, how are we doing? We've got 20 minutes. Let's at least get talking about the next section. Homework. I posted online. If you go into class files, I've put up here your homework schedule, which shows the problems that you should do. The only issue with this is that I have not completed the entire semester's worth of homework. This is Chapter 10's homework problems. I believe, if I'm not mistaken, Chapters 11 and on, I believe that the homework assignments are in the notes. So when we get to the end of the notes in class, they're there. So, but this is enough to get you started, all right? So just print that off and. So my expectation is that you would do that before next class. The homework. No, 10.1. Just 10.1. Yeah, no. That's just all of Chapter 10. If you're an overachiever, then go ahead. Yeah, I'm going to need you to come in on Saturday and take care of that, all right? All right, vectors. We've heard of vectors, yeah? And there's actually different definitions of vectors, because vectors, most students will look, when they're asked about a vector, they'll think of like some arrow sitting in, like on a sheet of paper or something like that. But a vector can be, there are vectors, functions can be vectors. So it gets more abstract. How many of you have taken linear algebra? Anyone taking linear algebra? You're taking it now? I think you can take them together, this class and that together. So you may in linear algebra see that a vector can be more than just what we're looking at here. So we call them, in this class, we're going to say a vector is an object, okay, that has, vectors are objects that have two main properties. They have a magnitude and they have a direction. That's all it takes to be a vector. It's something that has a magnitude and then it has a direction. Sometimes we call the magnitude the length, or it's also called the norm. And then the direction, that's a little tricky because direction depends on where you want to orient from, right? Like in what direction am I pointing right now in reference to this wall is one angle, but if I say in reference to this wall, it's different, or if I say reference to the North Pole, it's different. So we always have to have something to refer to if we're going to talk about angle. So in two-dimensional space, this is what a vector would look like. Right? We can change its direction, we can change its length. In three-dimensional space, the vector can be sitting anywhere. It's just like an arrow, has some sort of length to it, and it's pointed in some direction. Right? That's a vector. Now, some language behind these things. If you're given a vector, we're going to have an initial point, which is where it would start, and then what we call a terminal point, which is where it would end. The initial point we call the tail, the terminal point we call the tip. We also use a special notation for this vector. The book uses a bold, okay? So if they want to call this thing V for vector, the book will use bold V. But it's difficult for me to write bold on the board all the time, right? So instead of using a bold, we use this little half arrow above the letter to let you know it's a vector. This is referred to as a displacement vector. Two vectors are said to be equivalent or equal. So if we're going to compare two vectors together and say, are they the same? They only have to, the only thing that has to matter, or the only thing that matters, is that they have the same magnitude and the same direction. Position does not matter. So if I look at the vector below, the two vectors, these two vectors are equivalent because they both have the same length and they both have the same direction, meaning they're parallel to one another. And if I move them around, so if I take one of them and move it to the left, and let's say move it up, I have not changed it. It's still the same vector as the blue one. These are still the same because they're still the same length, still the same direction. Yeah? So why are vectors convenient in things like physics? I know that's kind of a general question, but what are vectors good at representing in physics? Forces, right? Because you can be applying a force as you're dragging something across the floor. You could be applying the same force the whole time. So the actual force isn't changing. It's moving through the room as you move through the room, but the force isn't changing. So the vector is a good way of representing that. We don't want to have to change our definition of the force every time we move a little bit because it's changed its position. So that's one of the useful parts of uses of vectors. So how do we determine a vector in two-dimensional space? So if someone gives us 2 points, right? 2 points in two-dimensional space, we need a way of defining the vector connecting these two together. And there's 2 of them possible. If we have 2 points, we can talk about the vector AB versus the vector BA. The vector AB means you start at A, you end at B. So A is the initial point, B is the terminal point. The vector BA starts at B, initial point, terminal point. So let's just talk about AB first. So let's see this vector AB. So I'm going to give you the coordinates of these points, all right? The coordinate of this point, the x and y coordinate, looks like -1, -2. And the coordinate of this one looks to be 2, 3. So how do we represent that green vector that goes from A to B? We subtract. What do you mean subtract? That's right, but
A from B.
A from B? You take A away from B? So take this one and subtract this one? How do you mean subtract though? Like
1 times
take that x-coordinate and subtract this x-coordinate.
x2 minus x1.
And then this one, take away this one. That's what's written down up above here in the notes right there. You're going to go from A to B. You go your second x-coordinate, which is the terminal point, subtract the initial point, x-coordinate, and then do the same for the y's. So you would get, let's see if I can line this back up. Yeah. So this would be equal to 2, take away -1 is what? 3. And then 3 take away -2, which is 5. But because it's a vector, we're going to use a special notation. We're not going to use this. Because the parentheses was for a point, right? For an ordered pair. This is not a point. This is a vector. So we use the angled brackets instead. If you put an angled bracket here like this, then that is now understood to be a vector instead of a point. What is the difference, though? I really want to make sure you understand. If I were to say, come in here and everyone plot this point, 3, 5. You got 3. You've got 5, right? You'd be somewhere around, I don't know, somewhere in here. 3, 5 is this point, right? 3, 5 is, the vector 3, 5 is what? It goes from the origin to this point, doesn't it? It has that length in that direction. This vector, 3, 5, is equivalent to the vector AB. Why are they equivalent? Same direction, same length, right? So there's a very, very big difference between these two things. Point versus vector. You can move this one around. It's a little arrow that you move around. This one is just a point. Now, what would the vector BA look like? Well, it would go the opposite direction, wouldn't it? And so it would how would we do the math here? Opposite, right? Instead of going 2 minus -1, we go -1 minus 2. -1 minus 2 is -3. And then we go -2, take away 3, we get -5. Those look similar, don't they? They do, don't they? They're just off by a sign. In fact, you could say this, couldn't you? The vector from A to B is just the opposite or negative of the vector from B to A. That's all it is. Are these two vectors equal? No. They're not equal. Because their directions are different, right? Their directions are different. One of them pointed this direction, the other one pointed this direction. Are these two vectors parallel? What do you think? We haven't defined parallel yet, so it's going to be, I'm just kind of asking you to take a guess at it. Do you think that these two vectors are parallel to each other? We'll see. Put that on the back burner. So if we're in three-dimensional space, then you want to go from A to B or B to A. It's the same thing that you do in two-dimensional space, except you have one additional piece that you have to calculate. You just have to get that third piece of the vector. Understand? Let's just do one of these. Let's do part B. Find the vector from B to A. So it's going to be a vector, so I'm going to use angle brackets. I'm going to have the three pieces in here. Now when you do this on your own, I hope that you'll know that you need to take one of these and subtract the other, but it's a matter of which order is it, right? That's the part that people usually mess up. So if I'm going to go from B to A, which one do I subtract from which one? subtract B from A. Is that, yes?
If you're going from B to A.
If you're going from B to A,
You subtract A from
you got to be careful on our language here. If I ask you to subtract 5 from 4, what does that mean? If I say subtract 5 from 4, does this mean that, or does this mean that? Which one of these is subtract 5 from 4, top or bottom? Bottom one. Subtract 5 from 4. Yeah, that's all. We just got to make sure we understand the language. If you're going to say that, you understand it, yes. That's good. So if you're going to go from B to A, you're going to subtract B from A. That means you're going to take A and subtract B from it.
I passed fourth grade, I promise.
I mean, it's just semantics, how you say it, right? I could say this two different ways, right? I could say take 5 from 4, right? Or I could say take 4 and subtract 5. I mean, you just need to know which one it is. I'm going to go from B to A. The way I always look at it is there's an arrow, right? And I'm going from B to A. I always like to just then go and say, okay, I'm going to start at A, and I'm going to take these B guys away from it. So I'm going to take this, and I'm going to subtract these. So I'm going to go 6, I'm going to take away 2, -5 take away 8, 6 take away 10. That's what I'm going to do. So what do I get here? 8. That's 6 take away -2. And then -13.
Isn't it the other way around?
Which way? -4. Nope, this is it.
So we're subtracting B from A, right? It's B.
You're taking, yes, you're subtracting B from A.
But isn't it BA should be B minus A?
No,
We're subtracting A from B.
no. If you're going to subtract A from B, then you're going to be doing this one. If you're one of those people who just likes formulas, which I'm not a formula memorizer, I mean, that's it right there. So if you label these points, I'll go slower. Okay, here's A, here's B. Let's do the one from B to A, so it's this one, all right? A is x1, y1, z1, so that's this point. This point is x2, y2, z2. Then if I want to go from B to A, I'm going to take x1, which is this one, and I'm going to subtract this one, which would have corresponded on the previous problem to taking the A1 and taking away the B part, right? Do I need to continue, or y'all got that? You got that? Okay. The zero vector. There is a vector that has no length and no direction. It's the zero vector. And it does get a bolt, or it does get the arrow on it. In R2, it's just the vector 0, 0. In R3, it's the vector 0, 0, 0. What do you think the zero vector is in R1? It is 0. It's the number 0 in R1. But we don't mess with the vector, zero vector. We don't mess with vectors usually in R1. We usually go from 2 and higher. So has no direction, has no length. Some language here, components. So when you're looking at a vector, if you go back and you look at, back when you were doing like ordered pairs and I put 5, 4, we would say 4 is the x coordinate. We'd say 5 is the y coordinate. With vectors, these things are not called coordinates, they're called components. So you'll hear me saying this throughout class. You know, we're going to be looking at the x component of the vector, the y component of the vector. It's just these two pieces in R2. And then in R3, it's these three pieces of the vector. So the components. We have what's called the parallelogram law. If you take two vectors and add them together, so I have two vectors here. I'm calling one of them u, I'm calling one of them v, and I'm adding them together. The way we add them together is that we paste the tail of one vector to the tip of the other one. So if I'm going to add u and v together, I'm going to take the tip of this one and attach it to the tail of this one. So remember, you can slide the vectors around, right? So I'm going to take the vector u, which this is blue one, and I'm going to take its tip and attach it to this tail. Whatever happens when I do that is what we call the resultant vector. So I will do that. Let me see which way I want to do it. Boom. And as soon as I put them together, as soon as I attach the tip of this one to the tail of that one, then I've created this path. Okay, starting out here, I go up through u, right? I add v, I go across like this, I end up here. So at the end, the net result of what happens here is that I'm really just going from this point to this point, which creates a new vector, which we call the resultant vector, which is what u plus v is. Now this is called the parallelogram rule because that's not the only way I could have done it. I could have also, let's see if I can do it this way. Let's see, could have done it this way. And where's the result here? Right up here? That's also the same vector. And if I put that u back where it was initially, no matter how I do it, I create this parallelogram, right? So this is actually v plus u, this is u plus v, but remember that addition is commutative, so it didn't matter the order in which I did this. So when you have two vectors and add them together, you create this parallelogram. And so they call it the parallelogram rule. What you need to make sure you understand is that u plus v is that vector, which is equivalent to that one. Right? Slide it up there, they're the same thing. Same length, same direction. Oh, I'm out of time, I'm sorry. How did that happen? I'd like to pass you your first mini exam. This is your first take home. 2, 3. You're free to start these. Go ahead and take that whole set and pass it over to the other table. Just keep that one there. You're free to start these. This test, it says on here, let me read the instructions if you're willing to hang out for another 2 or 3 minutes. Well, we're over here. These are online. There any more? How many did I print? I thought I printed enough. There are no extras? I thought I printed 28 of them. Okay, well look, in course files, does everyone see this? In course files, take-home exams. I have supplied you with the take-home exam that you have. I know some of you didn't get a copy. I apologize. I'll go down to my office if you want a copy right now. I've provided it in a PDF format, which is what that is. I've also provided it in the CDF format, which is the format that you can go and interact with. It says that this is due on the 8th. I'm asking you to work alone on this test. Sometimes I'll allow you to work together. Okay, this one I want you to go about it alone. You're to come to me for help. If you need help, I'm more than happy to assist you. Show all your steps, justify your answers. Order must be neat, right? Your work has to be neat, ordered and stapled. Box your final answer. Use the concepts from 10.1 to 10.5. So that's it right there. You can maybe start this. I'm not saying you could be able to do this yet, all right? But at least you have it now. Work on your homework. Have a good day. Sorry I kept you over so long. Pardon? Do what?
Would you watch any fun videos?